Hello, my name is Vint Cerf, and it's a pleasure to welcome you to this webinar on the Solar System Internet. My task is to give you a bit of an overview of where all this idea came from and where we are today. Others, of course, will fill in many of the blank spaces and provide a lot more detail. But let me begin by telling you a little story. Back in 1976, America landed two Viking landers, Viking 1 and Viking 2, on Mars. An extraordinary success considering the time period. And I remember being very excited about that. But then for about 20 years, until 1997, very few of the space efforts towards Mars worked out very well. Many crashed or missed the planet or burned up in the atmosphere. Until 1997, when the Pathfinder mission landed a little rover called Sojourner in a bouncing balloon. I remember thinking if I had been the program manager and the engineers had come in and said, we're going to deliver your $6 million rover in a bouncing balloon, I would have thrown them out of the office. But it was successful. It worked, and we got data back from that little rover. I got so excited when I heard about that I got in touch with the communications team at the Jet Propulsion Laboratory that was handling comms for that mission. And when we got together, we explored what we might think about trying to do that might be needed 25 years later. And we came up with the idea that we should be thinking about a solar system-wide internet to support manned and robotic space exploration. We thought at the very beginning, or at least I thought, that, well, we had internet running on Earth, so it ought to work on Mars. The TCP/IP protocol seemed to be doing okay at the time. This was 1998, remember. But then we started doing the math, and we realized that the speed of light was too slow. And that we knew this, of course, that when we're farthest apart in our orbits, respective orbits, Earth and Mars are 235 million miles apart. It takes 20 minutes for a radio signal going at the speed of light to make a one-way transit, and of course it's twice that to come back. Even when we're closest together at about 35 million miles, it still takes on the order of 3.5 minutes for the signal to get there and another 3.5 to come back. And at least I didn't think that the flow control schemes of TCP/IP would work very well with a 40-minute round-trip time. And there were some other problems, too, like the planets are rotating, and we didn't know how to stop that. So if you're talking to something on the surface and the planet rotates, you have to wait until it comes back around again. Similar problems with satellites that might be orbiting and are occluded by the planet itself. So we have a highly variable delay in this interplanetary environment, and we have disruption. So we concluded that we needed to think our way through what we call delay and disruption tolerant networking, or DTN for short. And as we explored these ideas, we began to try out some concepts. One of them was based on a file delivery protocol, the CCSDS, the Consultative Committee on Space Data Systems, together with the space agencies that make up that body, had come up with the CCSDS file delivery protocol, which was a mechanism for storing data in a rover, for example, or a lander, until a signal could be propagated back to the deep space network on Earth. Now, just a small pause here while we talk about the Deep Space Net. This was a brilliant step, a big investment made by the Jet Propulsion Laboratory with support from NASA to build 3 70-meter dishes in roughly 120 degrees apart in Madrid, Spain, Goldstone, California, and Canberra, Australia. The idea being that this big dish could reach out into the solar system to talk to spacecraft that were on their way to a planet or to a comet or possibly to go in orbit, or maybe even sending a lander or a rover. So way back in 1964, NASA was already thinking in very ambitious terms, in multi-mission terms, and that's a very important concept for you to hang on to. So coming back to 1997, the Jet Propulsion Lab team and I and others at MITRE Corporation began thinking our way through what a solar system internet could look like and what kinds of protocols we would need in order to support it. One thing we clearly realized is that because the links are not consistently available, unlike the usual case on Earth with a very dense and highly interconnected set of networks, in the interplanetary case, the links come and go depending on orbital dynamics. So we had to think about storing data in the network, which we did not do in the internet, to wait for a link to come back up again so we could transmit the data further in multiple hops to get to the destination. So storage in the network was one of the new ideas. The second thing we had to be concerned about is that because of the high variable delay, some of the normal tactics that were successful in the internet might not work for the solar system version. For example, if you think about the domain name system, the normal way in which a TCP connection is opened is first you look up the name of the host, the domain name of the host, like google.com, and you get an IP address back, and then you use that to open a TCP connection. Well, imagine you're sitting on Mars and you're trying to get to a destination on Earth, and you do a DNS lookup, and 40 minutes later you get an answer back. In today's world, that answer might be wrong because the device you're trying to reach might be mobile, and it may have gone from one radio network to another. It's gotten a different IP address, and so the data that you got back is out of date. So we came to the conclusion that we were going to have to do some serious re-engineering in order to make this system work across the solar system. The project gets started in 1998, and it begins just with a small group at the Jet Propulsion Lab and MITRE Corporation. But in the ensuing 20-some-odd years, 27 years or so, the effort has expanded not only to multiple laboratories of NASA, but also to other space agencies, the European Space Agency, the Korean Space Agency, the Japanese Space Agency, are all part of the Consultative Committee on Space Data Systems, whose job it is to standardize protocols that are going to be used in space communications. The same team that was working on this delay and disruption tolerant networking also thought it would be useful to get access to people who were familiar with the internet, and so they began work in the research, Internet Research Task Force, IRTF, on space communications. And as they got far enough along, it started to look like this was going to be a workable design. It was moved into the Internet Engineering Task Force for standardization. So over the course of the years, from 1998 to the present, implementations, prototype implementations, and finally standardized implementations of the bundle protocol, which is the label we finally attached to the primary protocol for DTN. That bundle protocol has become standardized both at the Consultative Committee on Space Data Systems and also in the Internet Engineering Task Force. A number of implementations have been made, but perhaps the most significant step in this whole story comes roughly around 2004. Now remember, we were starting to do this work, we're thinking about it in 1998, but by 2004, two more rovers, Spirit and Opportunity, land successfully on Mars in January of 2004. And the intent was to transmit data directly from the rovers to the Deep Space Network on a direct to Earth link at roughly 28 kilobits a second. There were some problems arising with that transmission, and in the course of debugging those problems, one of the JPL engineers recognized that there was an X-band radio on each of the rovers, and that we and others, NASA and ESA in particular, had sent orbiters to map the surface of Mars or to act as radio relays in order to communicate from the surface of Mars back to the Deep Space Network. And so at this time, this is 2004, there was a protocol called CCSDS File Delivery Protocol, which had been developed. It's a predecessor to today's bundle protocol suite. And that protocol was proposed to be uploaded to the orbiters and to the rovers in 2004 in order to use store and forward mechanisms to deliver data from Mars to Earth. So the idea was that when an orbiter came overhead, it would receive data coming from the rover, and then transmit that data back to the Deep Space Net when the orbiter gets to the right place in its orbit. So it would store the data and then forward it. So that was another important concept which influenced the design of the delay and disruption tolerant networking protocols, and that is storage in the network until the links could come up. So the CFDP has been serving the needs of rovers ever since 2004. So many of the other Perseverance and the other Spirit, Opportunity, Perseverance, and other rovers have been served by this store and forward method to the present day. In the meantime, a great deal of work has gone on to test and standardize the delay and disruption tolerant bundle protocol suite, which also includes a link level protocol that we call the link glider transmission protocol. And this was to honor and recognize JCR Licklider, one of the forerunners of the internet. He had sent in 1962 a letter to his colleagues telling them about his idea for an intergalactic network. Of course, it was tongue-in-cheek at the time, but what he was talking about is what became the ARPANET, which was the predecessor to the internet. And so we recognize Licklider's contributions with that identifier, the Licklider transmission protocol. We're coming back now to where we are. We have been through years now of implementation and testing. Multiple agencies have built instances of the bundle protocol suite. One of them at the Jet Propulsion Lab is called ION, or the Interplanetary Overlay Network. But there are several others as well, some operating on very small Raspberry Pis, some operating on larger platforms, and some are already functional in space, and so we have flight-tested capabilities. So what's important for you to recognize is that we are at the cusp of being able to launch an interplanetary internet, probably starting out with missions, for example, to the moon, which is the Artemis mission is a return to the moon, and then another mission, of course, will come to Mars and probably to some other places in the solar system. And as these spacecraft are launched and they complete their missions, they may be able to be repurposed as nodes of an interplanetary backbone network. So we could grow this system sort of mission by mission over time. At this stage of the game, it's 2025. We have the standard protocols, multiple implementations of them, and they have been tested in realistic environments. For example, we did one test with our colleagues at ESA called Meteron, which was to see whether the protocols could work in a real-time way when the distances were short. And so while a rover on the surface of Earth was controlled by astronauts who were on board the International Space Station, which is not very far away, latencies were very low, and so you could do real-time steering. Of course, that wouldn't work if you were on Earth trying to steer a rover on Mars because of the 40-minute round-trip time. But the idea was to show that the DTN protocols would work well in a low-latency environment. There was also a question about how much bandwidth you could push through that protocol, and so another test was done with an orbiter around the moon using an optical transmission and reception system, and that was demonstrated at some 600 megabits a second. So now we have a protocol suite which is capable of running in low latency and high variable latency at low speeds and at high speeds. A very, very rich and adaptive environment. So what are the implications of all of this? You'll learn a lot more about the specific details of the protocols that make up this solar system internet concept. But in this talk, I want to draw for you some of the implications of a successful implementation of a solar system internet. So the first thing I would observe is that we would like one of the properties of the terrestrial internet to be reflected in the solar system internet, which is that multiple parties could build pieces of the system and make them interworkable in the same way that multiple networks make up the global internet, tens of thousands of them at this point. So we want standards, and we want the ability to interoperate among different operators. We also need to make sure that the system is developed in a collaborative way. The internet wouldn't be what it is today if it were not for very intentional collaboration among government agencies and private sector players, and a whole ecosystem of organizations like the Internet Corporation for Assigned Names and Numbers, the Internet Society, the regional internet registries, the root servers, the Internet Engineering Task Force, the Research Task Force. There's just the Internet Governance Forum. There are a long list of organizations that have arisen out of the success of the Internet and contribute to its continued success. And I believe that a similar kind of ecosystem is not only needed, but will evolve, but it won't evolve naturally unless we work hard to make it so. So that brings us to very important policy questions that arise as you think about operations off-planet. So one possibility is that we will end up running little internets, lowercase I internets, on other bodies of the solar system, and we'll have to find a way to interconnect them if they are interconnected, let's say, on Mars. And so the conclusion we've reached is that if you are going to build small internets on other planets or other interplanetary bodies, if we're going to do that at all, we should use IP version 6 for that, because it has such a massive address space, and we can make sure that there aren't any address collisions assigned. Of course, it may be that we will end up building only bundle-aware software so that you don't need to worry about interconnecting to the internet. But on the terrestrial internet, there's a good chance people will not switch over to the bundle protocols, and so we'll have to build interfaces that will allow the terrestrial internet users to communicate with the extraterrestrial users of the bundle protocol suite. So there are several different possible architectural outcomes that we have to at least anticipate and prepare for. The more interesting question, of course, comes as you realize that commercialization of space is becoming a very important aspect of today's space world. Low Earth orbiting satellites are proliferating rapidly, Starlink being the most visible of them, but there are others that are coming. And so that's one clear commercialization step in this 21st century. Other uses of satellites preceded that. They were synchronous satellites, for example, for communications, and other satellites for Earth observation in order to get a better handle on what's happening to climate, for example, or to evaluate the condition of crops around the world, among other things. So we have a significant population of satellites, some of which are commercially provided as opposed to purely government-provided systems. And that's just in the cislunar space. We have the return to Moon in the Artemis missions and the Moonlight missions in Europe. Other countries, China, for example, and India and Japan, have interest in returning to space. And some of those interests are now commercial in nature. NASA began a commercial lunar program and said basically they would purchase capabilities, whether it was communications capabilities or habitats or rovers or other capabilities, on a commercial basis to be used in the return to the moon. So as we begin to see commercialization, a great many questions come up about policy and about disputes and how things will be resolved. At the moment, I can imagine a commercial operator learning that if he or she builds a mine on the moon, that that there will be a customer. NASA has said, we will buy the product of the mine. Of course, the natural next question from the CEO might be, can I own the property that the mine is on? And according to the Outer Space Treaty of 1967, the answer is no. No one is supposed to be able to own extraterrestrial property. Now, perhaps in the future that'll change, but at the moment that's the current going-in position. So the CEO now, hearing this, might still say, well, can I register my mine somewhere so that it's known that I am responsible or my company is responsible for operating it? And it's not clear where you would go to register this. What if there's a dispute about such a registration? Where would you go in order to resolve the dispute? Or worse, what if someone interferes with the operation of the mine? Where do you turn for help? And we don't have good answers to any of those questions, but I contend that we will need answers to those questions, and sooner rather than later, because many of these scenarios are likely to unfold within the rest of this decade, and certainly in the next one. So there are policy questions that need attention in addition to technical questions. We also want to make sure that, just as in the case of the terrestrial internet, operators of different components of the solar system internet can work independently but then collaborate and interconnect with each other. So there are concepts such as contact plans, where you create a list of communicating satellites or communicating nodes that know about each other and can therefore transmit data back and forth to each other. So you can imagine a grouping of nodes of an interplanetary network that know about each other and know how and when to contact each other, and with what protocols and radio frequencies or optical wavelengths and the like. So you can imagine that there are different collections of nodes that know about each other, that not all nodes of the interplanetary network necessarily know directly how to communicate with each other, in the same way that not every node in the internet knows how to communicate directly with another one. It gets relayed through multiple parties. And in the internet world, there are such things as autonomous systems, that's collections of nodes that have an internal routing capability and also have an inter-autonomous system routing capability. We call that the Border Gateway Protocol. So in the interplanetary equivalent of all this, you can imagine multiple contact plans that know about a collection of nodes. Those nodes can communicate with each other when it's timely. But then there may be some nodes that are in more than one contact plan, and so they can link the nodes of two different contact plans together. That concept is still in development, but that's a basis for cooperation and collaboration and sharing of communication resources among the parties that are building and operating components of the solar system internet. That's just the beginning of some of the policy questions that are going to come up, certainly within the next decade, if not in the next several years. And that's exactly why it's important for us to start thinking now about the policy issues that will arise and the instruments and agreements and maybe even institutions by which those policy matters will be resolved, in which agreements will be made. There is a beginning of that in what is called the Artemis Accords that were developed by multiple spacefaring countries that are part of the Return to the Moon Artemis mission, that are collaborating with each other. And there are other agreements signed by some, now I think over 50 countries and institutions, that are intended to build the basis for this kind of collaborative work, not only for communications, but for operations in general. So here we are, it's 2025. You're part of an important webinar looking towards the future, looking at the current state of our communications capability in space. This is a very exciting time to be around. If this were a novel, we're probably at chapter 2 in a 35-chapter story. But it's really fun, and I hope you'll enjoy being at the beginning, seeing how this is all going to evolve. So as they say, I can't see you in person, but perhaps we'll cross paths on the solar system internet.